Boop.
No, I have to.
Yeah, I just get lots of especially probably
All right, well, it's time for me to get started. I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class. Just ask you just guide our steps today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So today, talk to you guys about work and the work energy theorem. So the work energy theorem is one of the cornerstones of basic mechanics that you want to learn and how to use and understand. But just to remind us, definition for curve, C, parameterized by, let's say, T maps to R of T. And typically our R of T we use, X of T, Y of T, Z of T for the respective X, Y, and Z formulas for the parameterization. If the curve is parameterized by T maps to that for T1 less than or equal to T2, T less than or equal to T2, then the work done by F along C is W equals the integral of F dot dr. So this is just a notation for the work, all right? The integral of F dot dr. And specifically how that's calculated is integral from T1 to T2 of F of R of T dotted with dr dt. Another way to understand this integral is you could think of it as the integral from T1 to T2 of so the vector field F. So we're talking about the work done by a force field, all right? This force, it could be a force field. It could be a force that could be applied at any different point in space. For example, you could think about like wind, right? The wind blowing through a room, and if you're like a little sailboat or like a sailboat, little parachute man floating around in the room, then the wind hits you. That puts a force on you no matter where you are. So we could calculate the work done on a little parachute man by this wind force, for example. But anyway, the formula here would look like this. Well, let me use F1. So F1 dx dt plus F2. My bad, there's no vector on F2. Just F1, F2 dy dt plus F3 dz dt. So here I'm assuming that the vector field F has components 1, 2, and 3. So a lot of times you guys might see, you might have seen that used as PQR, for example, in Stewart. A lot of times they use P, Q, and R for the components of the vector field. I'm just suggesting 1, 2, 3, whatever. And so this here is actually what you actually have to integrate. Here the F1, the F2, and the F3, they have to be, you have to take whatever the formula is that defines the vector field, and you have to plug in the details of the path that you're finding the work along to do that. We'll work an example here shortly. Another notation for this, though, which is nice, is just to say that this is really F1 dx plus F2 dy plus F3 dz. This is the notation you'll see in a lot of calculus books because it gives a pretty good summary of how to do the calculation. All right, but how you actually do the calculation is to put in x, y, and z as functions of time and like flesh it out in that way. Geometrically, another way we could look at this, and this is important, is that the work is f dot t times ds. So it's the arc length integral. So that's almost immediate from the original formula up here. Let me kind of unravel that for you guys just for a second. What's dr dt? That's velocity, right? So you can write the velocity as the speed times the unit tangent. The speed times the unit tangent, but what is that? That's ds dt times the unit tangent. See, so if you can imagine plugging this formula in for the velocity right here, you just get the force dot the unit tangent integrated over the arc length. Yeah.
What does S stand for again?
Arc length. So, for what it's worth, the integral of a function with respect to arc length is just the integral of the function evaluated at the path times the square root of dx dt squared plus dy dt squared. I really didn't want to write this today, dz dt squared, but made me do it. So dt from t1 to t2. So like this is the so-called arc length integral. It's the integral of a function with respect to arc length along the same curve. If you're wondering what that means geometrically, if you can imagine, I can't really do it in 3 dimensions, but in 2 dimensions, if you had like a little path, this would be, now I'm really getting off track here, but if this is the curve in 2 dimensions, and we're plotting f like this, right, then like the area of this tent would be the integral of f dot ds. Yeah.
How are you going to do the integral with like c but no other parameter? Like typically, if there's a definite integral, you'd have.
Oh, but this is not a definite integral. This is the line integral, and so I'm defining this symbol by that formula. Yeah. And here I'm just giving you other ways to look at it. The other way to look at it, of course, is you're basically adding up the part of the force that's in the direction of the curve over the length of the curve. That gives you the work done. We'll actually use this formula in an example today in just a second. Before I do that, though, let me give you a concrete example here. All right, so here we go. We've got point 1, the origin, and point 2 over here. I crunched some numbers before class. Let me look at my numbers. Oh, man. Hold on a second. I almost forgot to give you guys, if you have an important attendance sheet, so if you could add a data there and do the honors, appreciate it. Okay, so suppose let's look at this particular path here. And we're going to go from 0, 0 over here to, let's say, 8.837, I guess, meters. I'm going to drop the meters, if you guys don't mind, just to reduce the clutter here. So I'm going to look at that path, and I'm going to calculate the work done if we go from here to here for the force, and the force we're going to look at, is force as a function of x and y. We're going to look at the force x squared y. All right. And I'm actually going to look at the work done by that force for 3 different paths. 3 different paths that all have the beginning point and the ending point the same. So like start, end. All right. So yeah.
So for your ending point, is that meant?
Oh, yeah. So sorry. Thank you. Good question. Others? Okay, cool. So curve number one, let us look at, excuse me. I know this is going to be an odd choice, odd choice of parameterization, but here it is. So we're just going to look at the line that goes from here to here, all right? Just that's my curve, all right? And the curve I'm going to first parameterize by, let us say, x equals to 8.66t. And of course, what's y? What's y for that path? This is kind of stupid, but y is 0. All right, great. So y equals 0. And for reasons that are by no means clear at the moment, 0 less than or equal to t less than or equal to 1.02. All right, let's start with that. So to calculate the work done by the force, we'll do that. So what that is the integral over the curve. And let me just get to the point here. So 0 to 1.02. And then I have to put in the formula for x, which is what? 8.66t. So I plug that in. I square that, all right? That's my x squared. What's my y? Y equals to 0. All right, great. Then, following my definition, I'm supposed to take the dot product of this with the velocity, which is dx dt comma dy dt. Now here, that's just what? 8.66 comma 0. And then I take the dot product, and I get myself integral from 0 to 1.02 of, it turns out, 8.66 cubed times t squared dt. You do the calculus, and out pops 229.7. All right. That's what that integral works out to. Now, the units here are actually joules. It's actually 229 newtons per meter, newton meters rather. If I was to put back the units in here at the final step, this would be a newton meter. That's what you get. So that's one. We could calculate the work done. Now, nothing really happened with y, did it? Nothing at all happened with y here whatsoever. It's kind of silly in that regard. Another parameterization. So let's double speed parameterization for C. So here, another way we could look at C is x is equal to, what's 2 times 8.66? 17 point something or other. 17.32. Yeah?
Where did the 8.66 come
Oh, I didn't say. 17.32. I just made it up. 17.32. The reasons for it will become clear in the third part of this example, so just hang with me. 17.32t and y equals to 0. That's another way we could parameterize this horizontal line. All I did was I doubled the velocity. So if I do that, I have to do what to the time? I have to cut the time in half, right? So that's a 0 less than or equal to t less than or equal to 0.51. All right. Then I can calculate the work done. To separate these different cases, let me call this W1. Let's call this W2. Because ostensibly, it could be different, right? So you're integrating over the curve of f dot dr. So this is the integral from 0 to 0.51. We plug in 17.32 t squared, comma 0. We take the dot product with the velocity, which here is 17.32, comma 0 dt. So what's going in the second thing, I'm, just to be clear, what I'm doing here, guys, is this is what? This is dx dt, dy dt, okay? That's what's going there. And what's this give us? This gives us the integral from 0 to 0.51 of 17.32 quantity cubed times t squared dt, which, guess what? Works out to 229.7 newton meters when I put the units back in. All right? Now, this is not an accident. This is just a theorem of like calculus 3. if we have a specific curve, all right, like in this case, the line segment that goes from 0, 0 to 8.83, if you have just a particular line segment, and you were to parameterize it 2 different ways, all right, then assuming that you don't do any kind of funny business like go back and like cover the line segment twice in some kind of weird thing. If you just cover, if they're both consistent parameterizations, let's say, then for a static force field, the work is the same. So this is an interesting thing. It doesn't matter how, if the force field is static, so this does no time dependence, right? If the force field is static, a theorem of calculus 3 says that the work done from this point to that point along a given path, along a given curve, along a given set of points, will be the same no matter how you parameterize it. The proof of this ultimately just rests on like doing the u substitution, a change of variables. If you reparameterize the curve, you end up, by the u substitution theorem, getting the same formula for the work. So in your calculus 3 class, this is super nice because it means that it doesn't matter how you get from point A to point B for a static force field and a given set of points that connect those 2 points. The work is unambiguously defined using any parameterization. But in this course, it becomes something kind of interesting because it says that the work done by a static force field along a given set of points is the same no matter how you go from point A to point B, whether you go at speed 8.66 or you go at speed 17.32. Even if you were to do a variable speed thing, if you were to go such that you're starting out slow and like increasing like parabolically, like faster, 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 approaching the other point, it would still work out to 229.7. This is a fact of calculus. Now what's more interesting is when it's possible for the work done by a given force field to be the same for different curves, for different paths. So like a different path we might travel, and this will explain the source of the mysterious 8.86, is we could say projectile motion, right? Like, let's see what happens if we, follow this path followed by like a baseball, launched at 30 degrees. So if you go with v naught equals to like say 10 meters per second at an angle of 30 degrees, guess what? That gives you x is equal to 8.66 t. That's why I did that. So this is actually the end point for if you have projectile motion under, surface of the Earth, usual story, no friction. You'll go 8.83 meters over that away. And the so the third, and this is of course a different curve now, so let's call it C2. You'd have x equals to, goodness, 8.66 t. You'd have, now y is not just 0 now, right? Y is changing. We found how to find the parameterization though, right? It's what? It's, if I put the origin at the start, we've got v naught sine of 30 times t, which is 0.5 times 10, which is, so we got 5t, right? Minus 4.9 t squared. So there's your, these are the parameterizations of that parabolic trajectory. And let me adopt the let me start doing things the way you guys like to do it. So we can write dx is 8.66 dt, and we can say dy is equal to 5 minus 9.8 t times dt. So we can take the differential of x, we can take the differential of y, and then actually the notation that a lot of people like to use, and it's a good notation, f dot dr, for this one, we can write formally like this. It's the integral over the curve of x squared dx plus y dy. X squared dx plus y dy. And then what you do is you just plug in what dx is, you plug in what dy is, and you replace x and y what they should be according to the parameterization of the curve you're calculating the work over. So this one, integral from 0 to 1.02, because by the way, that's how much time it took for it to come and crash back down to the Earth. I worked it out, all right? So like if you plug in if you try plugging in t equals 1.02 into my parametric formulas, you'll get like 8.837 and basically y equals to 0, all right, to within about 1%. So anyway, x squared is 8.66t. I square that thing. I multiply by dx, which in this case is 8.66 dt. And then I add my y, which was a little bit ugly, but 5t minus 4.9t squared. And then I multiply by my dy. My dy here is 5 minus 9.8t, and then there's a dt here as well. So we have an integral from 0 to 1.02 of, like a quadratic, maybe a cubic. I think it's quadratic. Guess what it works out to? What's that?
Nope, I'm wrong.
229.7 would be correct. That is what it works out to, Newton meters. That's because this vector field, this force field, has a property which is called path independence. Let me give you a definition of that. F is, let's say F has path independence on U, all right, which is a subset of, let's say, Rn. So we want to either think, we pretty much either want to be able to think two-dimensionally or three-dimensionally, but I'd rather give one definition for both. So basically ends 2 or 3. Path independence on U if for any coterminal paths. What's a coterminal path? Coterminal paths. C1 and C2, we have the integral over C1 of f dot dr equals to the integral over C2 of f dot dr. So coterminal, let me draw a picture for you. So there's a universe in which we're living. That universe is U. That's the context in which the discussion's happening, all right? The domain of the vector field, if you will. And so coterminal paths are just paths which begin and end at the same pair of points. So like this could be C1, this could be C2, for example. Something I should mention is the work done depends on the direction that you're going, right? Like you don't talk about the work done on a set of points where you don't have, the set of points has to be oriented. There has to be a beginning and an ending. So that's why we draw little arrows like this to indicate that's the direction, okay, the direction of the path. So path independence. So I don't know for sure that this vector field's path independent, right? But it looks like it conceivably could be. Here's two different paths, two different curves with the same ending points, and we got the same work from both, right? Yeah.
So is this explaining that if a mass takes, a force takes a mass, say, at angle 30 degrees, and begins at the same point, ends at the same point as one that's going straight, no angle, they have the same work?
This particular force, it shows that, but if it's a different force, it might not. It's not true for every force. There are forces that are path independent. There are forces that are not path independent. Here, let me show you a somewhat esoteric but very physical example. This example would be completely inappropriate for Calculus 3, but it's completely appropriate here. So example 2. So suppose you got a plane, right? And you got a box, and it moves along this here circuitous path, all right? This curve C, it's in some plane, and you're moving this box along this curve C, all right? All right, and the plane has friction. So let me draw the box. I'll draw it here for my convenience. All right, so you got a box, a great picture of a box, right? And you're moving it along this curve in this direction, right? As you're moving the box, which direction does the friction force point. Okay, so let me see here. So how about this? This would be t, right? The unit tangent points in the direction of the curve, right? So if the box is down here, my boxes are deteriorating, but so this would be the direction of the unit tangent, right? It points in the direction of the curve where you're going. Where does the friction force point? Opposite the motion, right? So the friction force would point like so, or like so, right? So we can ask the question, for a box of mass m, coefficient of friction, is mu times what? Now, if there's nothing else in play, the free body diagram is kind of boring in the vertical sense, right? You've either got what? Normal force up, or mg down, right? So the normal force is equal to mg here. Force of friction, just mu mg, right? What's the direction? So like a formula for it is this. The force of friction as a vector is minus mu mg times the unit tangent. See, because it always points opposite the tangential direction. So that's straight up a formula for it because it's a unit tangent, so that's the magnitude times its direction. What's the work done by this friction force over the path? Let's calculate it. So we've got the work done by the friction force is the integral of the force of friction dot dr over the curve. But that's the integral of minus mu mg t. And I'm going to use the formula which is most convenient for this, which is the fourth formula I wrote on the left board, the one in terms of the arc length integral, you see. So we can also write this as dot t with ds here. And that's sometimes a convenient formula. It's very geometric. Get straight to the point here. T dot t is 1. Mu mg is a constant. So you can pull outside the integration. Integral of, so you got minus mu mg integrated over ds. What's the integral of ds over c, do you think? What's that purple definition I wrote on this board? Everybody should have seen the arc length discussed in Calc 2 by now, I think. Or Calc 1. Somewhere you should have seen arc length calculated. If you drop the f here, this is just the integral of arc length of the path. It's the distance traveled. We talked about this already, actually. Yeah? So that's just distance traveled, which of course is just what? Minus mu mg. We could call it the length of the curve, right? And so there you go. That's the work done by the friction force. It's simply mu mg times the length of the curve, right? And there's a minus because why? Because it's going opposite the direction of motion everywhere, right? So move along here. So another example that I could give you guys, pretty simple. Suppose we've got an inclined plane. We start with the box at the bottom of the inclined plane. The inclined plane has angle theta, and it goes a distance d up the inclined plane, right? So there's the end point there, d. What's the work done by gravity during this motion? Okay. So in this case, we can fall back on the simpler formula that I shared with you guys last class, right? Which is the work done by gravity is just what? It's the force of gravity, which is what? 0 minus mg, right? Dotted with the displacement vector. So I'm just pointing the displacement vector. It would be like this, right? Where's mg? Well, I guess, I don't know. I'd worked this out a different way before class, but it occurs to me I could just write down the components of d. What are they? Can you tell me the x and the y components of the d vector? D cosine theta, d sine theta. Great. So what's the work done then? Minus m g d sine theta. That would be the work done moving a box. Well, the work done by gravity. All right. So, listen, I have more of these calculus-based work examples to show you, like next class. But I don't want to do any more at the moment because it needs to sink in, and you should try to do some yourself. See if you can understand it. You really just have to follow the definition in terms of the calculation. That said, we are going to find a workaround. And so before we do too much more, I really should do a couple things. There's two things I need to do. The one thing I need to do is to explain to you why this is physically interesting. Because at the moment we're just calculating this integral, which is like y, right? The reason for this ultimately rests on conservation of energy. And it takes me about a week of class to properly derive this. So you're going to have to be patient. We're going to get to it, all right? But we're not there yet. But ultimately we get, for a conservative force, if the net force is conservative, rather, we get the energies conserved for the system, and then we can solve many of the problems we've been solving up to this point in a far easier way, which should be happy news. But in order to do that, we also have to understand a little bit more calculus that you guys maybe don't know yet. So I'm going to start with the work-energy theorem, and then I'm going to shift over to the calculus that you don't know yet, okay? So what's the work-energy theorem say? What is the work-energy theorem? So definition, mass m with velocity v has kinetic energy and I'll use Ke now. I should warn you. Dr. Buderas doesn't like this notation. He was telling me about it, how it's one of his pet peeves, and I was like, oh, because it's a notation I use. But it is weird. It's a variable with two letters. Like, that's weird. So if you don't like that, you could use T. A lot of people use T in higher physics for kinetic energy, because I mean, obviously T is kinetic energy, right? So 1/2 mv squared is the formula for kinetic energy. All right. So here's the interesting thing. Theorem. If F is the net force on M, then the work done by F from position R of, say, T1 to position R of T2 is the change in the kinetic energy. So it's the kinetic energy at 2 minus the kinetic energy at 1. This is the work-energy theorem. The work-energy theorem says that for the net force, the work done tells you the change in kinetic energy. Now, you can see why that would be interesting, because then kinetic energy is directly linked to speed, and we're interested in speed, right? Or velocity, magnitude of the velocity. So why is this true? We'll calculate the work done by the net force. So here we go. Integrate over C the net force dot dr. So that's going to be the integral from T1 to T2 of F of R of t dotted with dr dt dt. Please someone ask me if this is on the test.
Is it on the test?
Yes, since you asked. No, I don't know, maybe. I've asked it on the test before. This derivation we're going through is not bad. Wait a minute, I'm asking the wrong things. I don't have an Alexa at home, but I have one here. Alexa, is this on the test? Didn't work. Oh, I tried. Sorry, it's a quasi-inside joke. I'll stop. So integral from T1 to T2. I'm not going to explain the joke. You'll have to find somebody who can explain it to you. But if this is the net force, what do we know about the net force? What's that? Sum of all the forces. True. Very true. What else? That's essentially the definition of the net force, right? That's good. There's some particular equation the net force satisfies. What is it? Mass times acceleration, right? Newton's second law. So that's what makes this force different from all the rest, is it's equal to m times a. But a is dv dt, right? So you got m dv dt dotted with what? Well, dr dt is v dt, right? Check this out. If we take the derivative of v dot v, what do you get? Do you guys remember the product rule? So, yeah, we get dv dt dot v plus v dot dv dt, right? So check it out, right? This is the integral from t1 to t2 of the total derivative of 1/2 m v dot v. See, because up here we have 2 v, well, we have 2 dv dt dot v. So you see how this goes? If this right here, this guy and that guy together are that, right? Divide 2 to the other side, I have 1/2 of v dot v. The m just rides along. But then what? It's what? It's the derivative of, it's the integral of a total derivative. So by the net change theorem, that's what? 1/2 mv squared, right? Oh man, my m just became a w, that's not good. mv squared, you know, evaluated from, you know, t1 to t2. In other words, it's 1/2 mv2 squared minus 1/2 mv1 squared, which is, of course, kinetic energy at time 2 minus kinetic energy at time 1. And that's the work energy theorem. It says that the change in kinetic energy is given to you by the work done. Right? Any questions? Yeah? Oh, I thought he had a question. All right.
Yeah, because that's
So, yeah?
Can you explain real quick the blue underlined sections, how you get to the next one?
I'm solving for if we solve for dv dt dot v, dv dt dot v is equal to 1/2 of v dot v. And not just that, but it's the derivative of 1/2 of v dot v from this. So I have an m here, so I pull it inside and I get that. That's all. So there's some vector fields which have this path independence. There's some that don't. The only time we can use the work energy theorem is when we're dealing with the net force. All right, so it's consistent too. Like, let's think about this conceptually for a second. What do you know if the, let's think about this. If the velocity doesn't change, right? Or if the speed doesn't change, right? Let's say that. What's the change in kinetic energy if the speed of the thing doesn't change? The change in the kinetic energy is 0, right? So there should be 0 work done if the speed doesn't change. And I can think of a couple different situations where that's the case. The one case would be like, you know, the acceleration 0, so it's just constant velocity motion, right? Another case would be like circular motion at constant speed. In that case, what's the deal with the net force? The net force is not 0. Constant speed, circular motion, the net force is like so, right? Where's the tangential, where's t going? If it's this kind of circular motion, t is like this, right? So what's the deal with t versus the net force? Remember, the net force has to be center seeking, because if we're going in a circle, we must have mv squared over r for our net force in constant speed for the constant speed case. So in the constant speed case, yeah, of course the work done by the net force is 0 around a circle, because it's not changing the speed. Now, if on the other hand we were speeding up, right, if there was a dv dt, I mean if there was a change in the speed, right, if there's a tangential component to the acceleration, then there would be work being done by the net force in that situation. All right, and likewise the speed would be changing. All right, let me go on here. So we must begin our discussion of calculus of several variables. Up to this point, we have managed to make do with just real calculus. Like even this work integral that we did, yeah, it's a new thing, but we didn't really need anything except for dot product and things we've already done. But this, what we're about to do, is genuinely new, but it's not bad. And so the things I need to talk to you guys about are partial derivatives. What are partial derivatives? So definition, partial f, partial x means differentiate with respect to x, holding other variables constant. Now I could give you a more precise, mathematically precise definition, but I'd just like to give you a working definition. This is how we actually take partial derivatives. We differentiate with respect to x, holding the other variables as if they're constant. And so what does partial f, partial y mean? It means differentiate with respect to y, holding other variables constant. What do you think? I think you know where we're going with this. What do you think partial f, partial z means? Same story, but with z instead, all right? So we differentiate with respect to z, holding the other variables constant. So that's the starting thing I need to talk to you guys about. So let's look at some examples. This will be by far the easiest thing we did today, without a doubt. So you guys tell me, what's the partial derivative with respect to x of, say, x squared y plus y? I've got a 2x, and there's got a y there, because the y rides along, all right? So when we differentiate with respect to x, the y is a constant. It just hangs out there, right? So just like if you had x squared times 3, you'd get 2x times 3. So 2x times y, since y is a constant. Now the y, on the other hand, gone. All right? Partial y, how's this go? Same expression, but with respect to y, what do we got? Differentiating with respect to y, x is constant, so the x squared pulls out. We get x squared times y, with partial y, x squared times 1, which is just x squared, and plus what? Plus 1. We really taught you partial differentiation in Calculus 1 if you search your heart. You remember those problems we did in Calculus 1 where you had like A, B, and C floating around and you're supposed to treat them like they're constants? That's partial differentiation. That's all that is. Now the next question students will always ask is like, what are these funny symbols, right? So these are the notations for partial derivative. The distinction between partial and total derivatives is when you're taking a total derivative, you know the thing you're differentiating is just a function of that one independent variable. Partial differentiation, on the other hand, involves taking the change in one variable, holding another fixed. And if you had different choices of variables and you held different things fixed, you'd get different rates of change. So like it matters in the sense that saying it's a partial derivative announces to the other people that you're taking a differentiation of a function of several variables holding one fixed. And even this and that is somewhat ambiguous. Like to really be rigorous with a partial derivative, you should announce to the people that what the other variables you're using are. To be completely rigorous, like you can't take a partial derivative unless you explain what the whole set of variables you're using is. Let me shut up about that. Example 5. Let's try partial x of e to the xyz and partial y of x. Let me put an x there. Xe to the xyz. Partial z of x e to the xyz. I think if you can see the contrast of how each same expression, different partial derivatives, I think that's a good way to learn if you didn't know already. So here we have a function of x times a function of x, right? So we have to do the product rule. So we get e to the xyz plus x times e to the xyz, and then we have to multiply by the derivative of xyz times that. So that puts a yz here. So what's going on here is product rule. The partial derivative of x with respect to x is just 1. So I get that times e to the xy, and then I get plus x times the derivative of e to the xyz, which because of the chain rule brings down a yz here. So the next one, I'll write a step for the next one. The next one, x pulls out, and then we have e to the xyz, and then chain rule says I must multiply by the derivative with respect to y of xyz, which is what? That just pulls out an xc. So I get x squared z e to the xyz. It's that one. And then next, again, x pulls out. We have e to the xyz times partial z of xyz. And that differentiates just to xy. So we've got x squared y e to the xyz. So these are partial derivatives, all right? Now, why do we care about partial derivatives? All right? Great question. So the answer has to do with what we can do with the partial derivatives. We can use these partial derivatives together to form something called the gradient. So definition, the gradient of a function of two variables is by definition partial x, comma partial f partial y. The gradient of a function of three variables, it's a three-dimensional vector, partial f partial x, partial f partial y, partial f partial z. So depending on whether you're in 3 dimensions or 2 dimensions, you have a gradient, which is a two-dimensional vector field or a 3-dimensional vector field. So this is the gradient of a scalar function. All right? And obviously we won't get too far into it, but here's the definition. If f is equal to minus the gradient of u, then f is conservative vector field. Now, I'll state that more carefully next class, but that's basically it. If the force can be written as the gradient of a potential energy function, there's a minus out front because this is physics. It turns out that if that's the net force, then there's something called the total energy, which is conserved. Now, the vector field, it also turns out that if the vector field's conservative, it has that path independence I talked about. So the function, let's just, the final thing for today. What was the vector field we looked at today? What was it? X comma x squared y, right? If you look at it, that's minus the gradient of the function minus 1/3 x cubed minus 1/2 y squared. So the gradient of this guy right here gives you that vector field. That shows you that, in fact, the vector field we calculated the work by 3 different paths today is, in fact, a conservative vector field, because this right here is its potential energy function. So anyway, we're not done talking about these things, obviously. So have a good weekend, you guys.
I didn't do it last semester, so.